Hi guys, my name is Vinay Jain and today we're going to be discussing Leetcode question 104, maximum depth of binary tree. So what is the question? Given the root of a binary tree, return its maximum depth. A binary tree maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So what does the question mean? We have to find the maximum depth. And what does maximum depth mean? Let's say this is the binary tree we have, for example. So this is, let's say, depth 1. When we go one depth below, that is one level down. So these nodes, node 9 is at depth 2. Node 20 is also at depth 2. If we go one more depth down, so node 15 is equals to at depth 3 and node 7 is at depth 3. So this is what we have to find, the maximum depth. So that is essentially the longest route from the root node to the farthest leaf node, which is this. So we have to find the maximum depth. How are we going to do it? We're going to be using a modified version of a depth first search algorithm to achieve our aim. So how does this work? Let's understand this via an example. So let's assume that this is the root node. This is the root node and this is from where we began our algorithm. So the root node checks whether it checks if it's a leaf node or not. If it's a leaf node, then we return 1. Otherwise, we check into its left and right subtrees for depths, which has the more depth. If the left subtree has higher depth or the right subtree has higher depth. So the left height, let's say I'm just denoting it by LH, is calculated by 1 because we have the current depth plus whatever depth is in the left subtree of this node. So let's assume this is where we recursively check into the left child for the depth. So a recursive call is made into the left child and then we check whether this left child is now a null node or a leaf node. It is a leaf node, right? Since it is a leaf node has a depth of 1. So therefore, since it's a leaf node, this returns 1 here. So this essentially means that the left height for the node 3 is calculated to be 2. 1 plus 1, that is 2. Now once the left recursion is completed for the left child, now the function at node 3 recursively checks for the right hand child. I'm just denoting it by RH, signifying right height, which is again 1, the height at 3 for the node 3. And what is the depth for this child node? What is the maximum depth there? So this recursive call is made into the right child, which comes here. Now the program evaluates whether this is a leaf node or a null node. It is neither of those, it has children. So then we again recursively check for the left height of this, how much is the left hand child's height for this node, which is again 1 for the current depth and whatever depth is at the child node. So this then recursively makes a call to its left hand child. Now at node 15, since it's a leaf node, right, it has no further children. So then this returns 1. So for node 20, left hand child's height is, or depth you can say, is 2. 1 plus 1, 2. Similarly at node 20 now, we evaluate the right hand child's height or depth. So right height is equal to 1, the current depth plus whatever is at the children depth. So we now recursively check into the right child of node 20, which is node 7, for the height for that, for the depth for that. And since it's a leaf node, this returns 1, since a depth of leaf node is considered to be 1. So right height for node 20 evaluates to be 2. So now node 20 returns which is the maximum depth. So for node 20, what is the maximum out of left hand side and the right hand side depth, which is left hand side depth is 2, right hand side depth is also 2. So max of 2, 2 is 2. So this is the value that is essentially returned by node 20 to its parent called node 3, and 2 is calculated here. Now when it is done, so now node 3 calculates the right height from, or the right hand depth from its right hand side child node 20, which is 1 plus 2, that is, 3. This comes out to be 3. Now that node 3 has also evaluated its both left and right child's depth. Now it calculates where does it have the maximum value. So what it does is it calculates max of its left hand child's depth and right hand child's depth. For this, left hand child depth for node 3 is 2, which we calculated here, and for the right hand child of node 3 the maximum depth is 3. So this is what is calculated here. So max of 2, 3 is 3. So that is the maximum depth for node 3, and since node 3 is the root node and we've calculated everything so far, so this value is then returned to its calling function, let's say the main function. So this is essentially the algorithm. I hope you understood this algorithm via dry run. Now let's look at the algorithm. What actually is the algorithm for this problem? So the algorithm is, if node is null, return 0. If you have a null node, then the depth for that is considered to be 0. If we have a leaf node, then return 1, because depth of a leaf node is considered to be 1. These are the base conditions for our recursive algorithm. As we said, we're going to be using a modified version of depth first search algorithm. So this is our base conditions. Next we check point 2, calculate left subtree depth, which is essentially LH, what I annotated above. So 1 for the current depth plus whatever recursively we calculate the max depth in left child. So we recursively make a call to the left child of the current node and check what is the maximum depth there. Once this function is finished evaluating, we then check for the right subtree depth, which I denoted above as RH. 1 for the current depth, and then we recursively calculate maximum depth in right child. Once we have LH and RH calculated, then from the current node we return the greater of the two depths, that is max of LH and RH. So this is essentially the algorithm that is used to solve this question. Now let's look at the time complexity of the algorithm. Since in DFS we make sure that we only visit every edge and every vertices once and not repeat that, so that is why the complexity of this algorithm is O of V plus E, where V is number of vertices and E represents number of edges. And this is the time complexity of the algorithm for this question. I hope you guys understood the question and the algorithm via dry run, and also the time complexity helped you understand this question very well. I'll attach the necessary GitHub repository links for the code for this problem in the description box below. Please feel free to check that out. Thank you for watching this video, guys. Have a nice day.